7.2 is relating the characteristics of an exponential function to its equation. So we're taking a look at some characteristics so that when you see an exponential function, you can identify what the equation might be, or some of the characteristics of the equation. So what we're going to do is we're going to enter these equations into our graphing calculators, and then we'll complete the table to do a bit of a comparison so that you can have the general characteristics for these. So the first one we're going to look at is f of x is equal to 2 times 5 to the power of x. So we have y is equal to 2 times 5 to the power of x. Okay, and we will graph that one. Oh, I still have my scatter plot on. So make sure you've turned that off from our last section. Okay, so now we will graph it. But I'm going to have to fix my window. Oh, this is responding very slowly. Okay. So we can do our window at, say, -10. Well, we can put it at 10. We can go up by 1s. And y minimum. And put it at -2, but we're not going to go past the 0. We can put this one up to 100. And yeah, we can go up by 10, see what the graph looks like. There we go. Okay. So you can see our graph is going up. Actually, I'm just going to fix the window on this one. I'm going to have that Y scale go up by 2 so that you can see where that graph cuts. I'm just going to zoom in a little. Okay. I'm at 0 and 49. Maybe I'll make my window a little smaller again, and let's make this just 2. Oops. 20. There. Okay, so you can see it cut at the 2 there, because I went up by 2s. So if you go to draw this picture here, if this is 2 on the graph, our graph looks like this. So our number of, and this should say, x-intercepts is 0. Y-intercept occurs at, remember that A, so it occurs at 2. We're going to fill in the rest once we fill in all of these, just like we did in the last section. So for the graph of y is equal to 8 times 3/4 to the power of x. And I'm just going to do this on the same one so you can see the comparison. So it's 8 to the power of 3/4, or 8 times 3/4 to the power of x. So you can see as it's drawing it, it has changed directions. And our graph crosses at 2468. So if this is 8 up here, our graph was going excuse me. Our graph was going like that. So number of x-intercepts, again, it's 0. and our y-intercept was at 0 and 8. So what if we have y is e to the x? So e is a constant known as Euler's number. It is an irrational number that equals 2.718, and it goes on forever. This number occurs naturally in some situations where a quantity increases continuously, such as increasing populations. So as you're working on some questions in this section, this will come up. This y is equal to e to the power of x. So all it is instead of writing out that number, because it's a number that continues on forever, it's kind of like pi, we use the symbol e. So on your graphing calculators, you can do this. If you put y is equal to, let's move down. I'm going to do it on the purple one so it shows up better. So your e is, if you use your second function and the divide sign, that is e. So e to the power of x. So when this one graphs, you can see it's a lot like our first graph that we did, except where the y-intercept is. And this y-intercept occurs at 1, because if I substitute a 0 in there, any value to the number, or to the power of 0 is going to be a 1. So it's a positive, it's increasing, like that. So it still has no x-intercepts and y-intercept at 1. So what do we notice about the domain of these graphs? All of these are, we can use any real number that we want to. Our range, they're all the same. As long as it is greater than 0, it'll work for these functions. Our end behaviors. These were all going from quadrant 2 to quadrant 3. Quadrant 3, quadrant 1. I did that in the last section too. Quadrant 2 to quadrant 1. But what changes in them is whether they are increasing or decreasing functions. So the first graph, when we go from left to right, our y value or our x values are increasing and our y values are increasing. So this is an increasing function. For the second graph, when we go from left to right, our y values are decreasing and our x values, while our x values are increasing. So because it's the y equals is the decreasing amount, then we call it a decreasing function. And if we take a look at the last one, again, both of the values are increasing, so it's an increasing function. So what we notice is our x-intercepts, our domain, our range, and our end behaviors are all exactly the same for every exponential function. So they are common to all exponential functions. Our graphs are increasing, so the first and the third graph are increasing, and they're increasing when our b values are greater than 1. So e is the same as 2.718, and remember this is the same as saying 1 times e to the power of x. So this is our a value and this is our b value. So just use this symbol, which means our functions are increasing if b is greater than 1. It's decreasing then when our b is a fraction, but greater than 0. Our b can't equal 0. Remember from the first section that we did? B can't be 0, but it can get close to 0, and it can get close to 1. So it's that fractional value. So it's decreasing if b is between 0 and 1. So basically if it's a fraction. Okay, so methods of finding that y-intercept. So if I have y is equal to 2 times 5 to the power of x on your calculator, if we hit the second and trace, which is, whoops, where did trace go? No. Second and trace, that gives us calculate. We want to find value. So x is equal to 0. Whoops. X is equal to 0, y is equal to 2. So if you want to find any value on there, if you wanted to find out what did y equal when x was equal to 7, you just put second trace, which is calculate, hit value, and put whatever x value you want to find out what the y value is. So we do second trace, which is calc button, and we want to do value, and then put whatever x is equal to 0, and it tells us y is equal to 2. If you do this by hand, we let x equal 0 and solve. So y is equal to 2 times 5 to the power of 0, which is y is equal to 2 times 1, so y equals 2. Okay. So example 2 says, determine if an exponential function y is equal to a times b to the power of x could be used to model this data. So basically they're asking, is this a exponential function? So if we take a look at this, our x is increasing by 1. Our y values are going from 2 to 4, 4 to 8, 16 to 32. So as our x's are getting larger, our y's are getting larger as well. So if we go this way, it's going 32 to 16. So if you remember finding common ratios, you always take term 2 divided by term 1. 16 to 8, 8 to 4, and then 4 to 2. So all of these can be reduced to a 2 to 1 ratio. So because they can be reduced to a ratio like that, then we can then it is an exponential function because it's increasing by the same ratio every single time. If we tried this one, so we went from 25 to 16, 16 to 9, so this one works. 9 to 4, 4 to 1. So for this one, we have, oops, that should be an arrow, 4 over 1, so that's 4. 9 divided by 4, which is 2.25. 16 divided by 9, which equals 1.7 repeating. And 25 divided by 16, which is 1.5625. So none of these ratios are the same. So this one then is not going to be an example of an exponential function. So what we look at here is the values of x. We check to see if the x value increases by 1, and the second thing you have to do is make sure there is no x-intercept. So we can't have, if one of these also had was equal to 0 and a value for x, then it's not going to be an exponential function. So when we look at the x, those are the two things that we'll look at. Are they increasing by 1, and is there no x-intercept? So ratio of consecutive y values. If all of the ratios will reduce to the same ratio, it's likely an exponential function. And our ratio is generally going to be our b value. There's going to be a couple of exceptions, but we won't come across so many of those. Okay, example number 3. It says match each function with the corresponding graph. So what we look at here then is we look to see, okay, is this going to be increasing or decreasing? What is our x-intercept? Or not our x, our y-intercept. Increasing or decreasing? So if it's increasing, then we know from our previous examples that to be increasing, oops, I just lost a page. I'm amazing when, oh, there we go. To be increasing, then, our b value has to be greater than 1. And to be decreasing, our b value has to be between 0 and 1. Okay, so if we take a look at y is equal to 3 to the power of x, our y-intercept would be at 0 and 1. We have a 3, b is equal to 3. Therefore, this one is increasing. Next example here. For our y-intercept, if we substitute a 0, so it'll be 0 and 1/3. Our b value is equal to 3. So this is increasing. It's easier to write. Example number 3. Y-intercept is going to be at 0 and 3. Our b is equal to 1/3, so that's between 0 and 1, so this is decreasing. And then the last one, our y-intercept will be at 0 and 1. It's a fraction, so b is equal to 1/3, so this is a decreasing function. Okay, so if I take a look at my graphs here. First example, my y-intercept is 1. This is a decreasing graph, right? Because my y values are getting smaller as I go larger with my x's. So this is a y-intercept of equal to 1 and decreasing. So that means that this has to be number 4, which is y is equal to 1/3 to the power of x. Example B, this is an increasing graph. So I look at my y-intercept, it's at 1. So which one had a y-intercept of 1 and increasing? That was example 1. So y is equal to 3 to the power of x. C is an increasing graph with y-intercept here at about 1/3. So that would make that number 2. So y is equal to 1/3 times 3 of x. So the last one, of course, will be the one that we're left with, which is example 3. But just to make sure, it needs to be decreasing, and we have to have y-intercept at 3. So it's decreasing, and y-intercept at 3. So this is y is equal to 3 times 1/3 x. Okay, so your questions are on page 448 to 453. Refer to that chart on the first page of these notes for finding your characteristics